Earth's protective shield, the magnetic field. This invisible force is crucial for sustaining life on our planet. Our planet is a blue oasis in the vastness of space, teeming with life. From the deepest oceans to the highest mountains, life thrives in every corner. But this life exists under the constant bombardment of radiation from the sun. Solar flares and cosmic rays pose a significant threat to all living organisms. Thankfully, Earth has a natural shield, its magnetic field. This field is our planet's first line of defense against these harmful solar and cosmic radiations. This field acts as a protective bubble, deflecting most of the sun's harmful rays. The beautiful auroras we see are a visible manifestation of this interaction. It originates deep within Earth's core, generated by the churning of molten iron. This dynamic process creates electric currents, which in turn produce the magnetic field. This invisible force field extends far into space, creating a region called the magnetosphere. The magnetosphere acts as a barrier protecting Earth from solar winds. Without it, life as we know it would not be possible. The magnetic field ensures that our atmosphere remains intact, allowing life to flourish. The magnetic field is not static, it is dynamic and constantly changing. It fluctuates in strength and even flips its polarity. These changes can have profound effects on our planet. These flips, known as geomagnetic reversals, have happened many times throughout Earth's history. Each reversal leaves a mark in the geological record. One such dramatic reversal occurred about 42,000 years ago, an event scientists call the Adams event, or the Lachon excursion. This event had significant impacts on the environment and life. This event offers a glimpse into a time when Earth's protective shield weakened, with significant consequences for life on our planet. Understanding these events helps us prepare for future changes in our magnetic field. The Adams event, a flip in the field. This event is one of the most intriguing episodes in Earth's geological history. Imagine a compass needle suddenly pointing south instead of north. This isn't just a minor glitch. It's a profound change in the Earth's magnetic orientation. That's essentially what happened during the Adams event. The magnetic poles reversed, causing a significant impact on the planet. The Earth's magnetic field underwent a dramatic shift, weakening significantly before eventually flipping back to its original orientation. This weakening made the Earth more vulnerable to cosmic radiation. This period of magnetic instability lasted for approximately 800 years, a relatively short time in geological terms. Yet it was long enough to leave a lasting mark on the planet's geological record. The Adams event is named after the British science fiction author Douglas Adams. His imaginative works have inspired many to think about the universe in new and creative ways. He famously wrote in The Hitchhiker's Guide to the Galaxy that the number 42 is the answer to the ultimate question of life, the universe, and everything. This whimsical idea has captured the imagination of readers for decades. While the connection to the Adams event is purely coincidental, it serves as a reminder that the universe is full of fascinating and unexpected mysteries. These mysteries challenge our understanding and push the boundaries of scientific inquiry. The Adams event, though occurring thousands of years ago, holds valuable lessons for us today. It reminds us of the dynamic nature of our planet and the ever-changing forces that shape our world. A world transformed environmental impacts. The weakening of Earth's magnetic field during the Adams event had profound effects on our planet. With a diminished shield, more solar radiation reached Earth's atmosphere. This increased radiation ionized the air, creating spectacular auroras that would have been visible across the globe, not just near the poles. The impact extended beyond beautiful light shows. The increased radiation likely led to a depletion of the ozone layer, which protects us from harmful ultraviolet radiation. This, in turn, would have exposed life on Earth's surface to higher levels of UV radiation, potentially disrupting ecosystems and causing genetic mutations. Section 4. Life on the Brink, the Adams Event and Extinction. The Adams event coincided with a period of significant environmental change and extinction events. Large mammals, known as megafauna, disappeared from many continents during this time. While the exact causes of these extinctions are complex and debated among scientists, the Adams event may have played a role. The increased UV radiation and environmental stress could have weakened populations, making them more susceptible to other threats like climate change and competition for resources. Interestingly, some researchers believe the Adams event could be connected to the decline of Neanderthals, our close human relatives who disappeared from Europe around the same time. However, the link between the Adams event and Neanderthal extinction is still a topic of ongoing research and debate. Section 5. Echoes in art. Did the Adams event inspire cave paintings? During the Adams event, with its intensified radiation and potential environmental upheaval, humans may have sought refuge in caves. Interestingly, this period coincides with a flourishing of cave art. Could there be a connection? Some researchers speculate that the red ochre handprints, a common motif in cave art from this period, might have been more than just artistic expressions. Red ochre, a natural pigment, has UV-blocking properties. Could these handprints have been an early form of sunscreen, a way for our ancestors to protect themselves from the increased radiation? Section 6. A silent witness, the ancient kauri tree. The story of the Adams event is not just buried in the past. Scientists have been able to piece together this event's details by studying a variety of sources, including sediment layers and ice cores. One remarkable piece of evidence comes from an unexpected source: a giant kauri tree preserved in a New Zealand swamp for over 42,000 years. The tree's rings, like a natural time capsule, recorded the atmospheric changes that occurred during its lifetime, including the period of the Adams event. By analyzing the carbon isotopes within the tree rings, scientists could track the fluctuations in Earth's magnetic field and the corresponding increase in radiation. This ancient tree provides a tangible link to a tumultuous period in Earth's history. Section 7. The future of our magnetic field. The Adams event serves as a reminder that Earth's magnetic field is not a constant. This event, which occurred around 42,000 years ago, was marked by a significant weakening of the magnetic field, leading to dramatic changes in the environment and climate. It can change, weaken, and even reverse. These fluctuations are part of the natural dynamism of our planet, influenced by the movements of molten iron within Earth's outer core. In fact, scientists have observed a weakening of our magnetic field by about 9% over the past 170 years. This gradual decline has sparked concerns and prompted extensive research to understand the underlying causes. Additionally, the magnetic North Pole has been drifting at an unusually fast rate. This rapid movement has necessitated frequent updates to navigation systems and has implications for migratory species that rely on the magnetic field for orientation. While this doesn't necessarily mean a reversal is imminent, it highlights the importance of understanding these magnetic fluctuations and their potential impacts. Researchers are continuously monitoring these changes to predict future trends. A geomagnetic reversal in today's world, with our reliance on technology, could have significant consequences. The effects could ripple through various sectors, disrupting daily life and critical services. Power grids, communication systems, and satellites could all be affected by a weakened magnetic field. The potential for increased radiation exposure and satellite malfunctions poses a serious risk. By studying past events like the Adams event, we can better prepare for the future and ensure the resilience of our technological infrastructure in the face of natural phenomena. This knowledge is crucial for developing strategies to mitigate the impacts of magnetic field changes on our modern world.